We're in physical chemistry, beginning chapter 9. This is section 1. We're talking about solutions in this chapter. A solution is a homogeneous mixture. It can have several components. Now, the first thing we're going to do is talk about the composition of a solution. Now, for this purpose, we're going to use a simplified notation here. 1 star means it is temperature dependent. 2 stars means it's temperature independent. So first we're doing mole fraction, 2 stars, so that's temperature independent. Mole fraction is just X sub I is equal to N sub I over N total. So remember, I is our analyte, our solute, and then N would be the number of molecules, or number of moles. 2, 1 star, this is temperature dependent, it's molar concentration. So that's C sub I, again I is our analyte, the solute. And that's just Ni over V for volume. It's the same thing as molarity that you learned in general chemistry. And then 3, mass concentration. That's 1 star, so mass concentration is temperature dependent. We're going to have pressure. That's not supposed to be pressure, is it? Hold on. Let me see if this sentence is right. Physical chemistry, we're in chapter 9 now, this is section 1. Chapter 9, we're talking about solutions. A solution is a homogeneous mixture. It can have several components. Now, first thing we're going to talk about is the composition of a solution. For this purpose, we're going to use a shorthand notation. We're going to say 1 star means that something is temperature dependent, and 2 stars means it's temperature independent. Now, first we're going to do mole fraction. 2 stars says temperature independent. Mole fraction X of I is equal to Ni over N total. I is obviously our analyte, or the solute. And then 2, molar concentration, that's 1 star, so it's temperature dependent. So the concentration of I is equal to Ni over V. Remember, V is volume, and then I is our solute. And then this would be the same thing as molarity. And then 3, we have mass concentration. That's 1 star, so it's temperature dependent. Mass concentration is rho sub I equals Mi over V. So it's mass divided by volume. And then this is useful when you have polymers or something, if you don't know what Ni is, or if you just don't know what the molecular weight is. The fourth one is molality. That's 2 stars, so it's temperature independent. Molality, notice we're using M for mass up here, but M for molality down here. So pay attention to context so you know what you're looking at. And that's Nb over Wa. So in this case, B is our solute. So it's the number of moles of our solute divided by the weight of our solvent. And then also, so we could write it as the molality of B is equal to Nb over Na. So it's the number of moles of A times the molecular mass of A. This isn't Avogadro's number. Remember, this is the number of moles of A. And then 5th, we could talk about weight percent. And that's 2 stars, so it's temperature independent. Weight percent is just going to be the weight of B divided by the weight total. And obviously, in this case, B would be our solute times 100%. So this fraction here, this is called the weight fraction. And this is the common way that stock chemicals are done. Continuing on in physical chemistry, chapter 9, we're in section 2 now. We're talking about partial molar quantities. Now let's say we have the moles of substance 1 is N sub 1, the moles of substance 2 is N sub 2, the moles of substance 3 is N sub 3, all the way to, if we have R substances, we'll go to N sub R. Then we're going to say the V sub M star is the molar volume of the pure substance before mixing. So a star means either the pure substance or the collection of pure substances. For example, the total volume V star is the total volume before mixing. To find the total volume, if V star is equal to just the number of moles of 1 times the molar volume of substance 1 star plus the number of moles of substance 2 times the molar volume of substance 2 star all the way to the number of moles of substance R times the molar volume of substance R star. Now, then just plain V, that's going to be the total volume of our solution after mixing. Now, generally speaking, V star won't be equal to V, even if we're at constant temperature and pressure. For example, let's say we have 50.0 milliliters of alcohol and 50.0 milliliters of water. Now, V star is just 50 milliliters plus 50 milliliters, so we get 100 milliliters. But if you actually mix them together, it's going to shrink a little. We'll get V is equal to 96.5 milliliters. Now, V cannot be greater than V star for several reasons. One is because of the way the intermolecular forces work. We don't have time to explain that, but basically it's attractive, they'll attract, they'll shrink. And then the molecule size, if you think about it, if you have one that's big and one that's small, the small one will fit in between the big ones, so they'll squeeze in a little bit tighter. And then of course the shape too. If you mix molecules of two different shapes, they'll actually fit in together better than if you have all molecules of the same shape. Continuing on physical chemistry, chapter 9, we're in section 2. Other extensive quantities, remember, are S for entropy, G for Gibbs free energy, H for enthalpy, A for Helmholtz free energy, and U for internal energy. So U, we could say that's a function of temperature, pressure, and the amount of substance 1, the amount of substance 2, all the way to the substance R, if we have R substances. And likewise G, we could say that G is a function of temperature, pressure, the amount of substance 1, the amount of substance 2, etc., all the way to the substance R, if we have R substances. Now, if we have V, we can write the total differential dV as the derivative of V with respect to T, holding T and N constant with respect to T, plus the derivative of volume with respect to pressure, holding temperature and the substance is constant, dP, plus the derivative of volume with respect to N1, holding Tp and all other substances constant with respect to dN1, etc., all the way up to the derivative of volume with respect to substance, the amount of substance R, holding Tp and all other substances constant times the differential of the quantity of R. Now, partial molar volume, we're going to write that is a V bar sub J, and that's going to be equal to the derivative of volume with respect to the number of moles of substance J, holding temperature, pressure, and all other substances constant. But be careful of symbology, because in other books they'll use V var to mean average or molar volume, which is just V over N. So don't confuse those two if you're using more than one book to learn this stuff. So let's say we graph volume against the number of moles here of our solute, the analyte we're looking at right now. Notice how it's going to be shaped like a parabola facing up. So V here, remember, this is the total volume of the solution. And as you can see, there's going to be a place where it'll come to a minimum at a certain quantity. Now let's say we have the V sub I, that's the partial molar volume of substance I, and that's equal to the partial molar volume of I holding temperature, pressure, and all other substances constant. Now we're going to set dT equals 0, which means we're going to be isothermal process, and dP equals 0, which means isobaric process. So we're both constant temperature and constant pressure. Then we're going to say that dV is just equal to the Vj, the molar volume, partial molar volume of substance J, times the change in the amount of substance J, if we're adding some J. Continuing on physical chemistry, chapter 9, we're finishing up section 2 now. So again, we can write the exact differential of volume, dV, as the derivative of volume with respect to temperature, holding pressure and the number of molecules constant, dt, plus the derivative of volume with respect to pressure, holding temperature and the number of molecules present times dP, plus the sum of the partial molar volume of substance I, dNi. Now remember, we said V star is the total volume before mixing, and that's calculated just by adding up Ni, the amount of substance I, times the molar volume of I star, which is the unmixed molar volume of I. And then V is the total volume after mixing. And that's also from a sum of all the substance I, the quantity, times the molar volume of substance I. Now, then the change in the volume from mixing is just going to be equal to V minus V star. So we'll just subtract those two sums. The sum, the number of molecules, times the molar volume of I, minus the sum of Ni, the number of molecules of substance I, times the molar volume of I unmixed. Star is unmixed. We can factor out the Ni from those two then and say that the change in volume from mixing is just equal to the sum of the Ni times the molar volume of I mixed minus the molar volume of I unmixed. Now remember, we said before that volume is less than V star, but that's only if you're at constant temperature and pressure, so be careful with that. So U sub I bar is going to be the partial molar volume of internal energy, and likewise H sub I bar is going to be the partial molar enthalpy. And likewise G sub I bar is the partial molar Gibbs free energy. And that's defined as the derivative of Gibbs free energy with respect to the number of molecules of I, or the change in the number of molecules of substance I, holding temperature, pressure, and all other substances constant. This is the important one. And the reason is because it's equal to our chemical potential, mu sub I. Physical chemistry, we are finishing up we're in chapter 9, we're finishing up section 3 now. So let's talk about mixing quantities. For example, the change in Gibbs free energy from mixing is defined as just G minus G star. Remember, G would be after mixing, G star would be unmixed. Same with the change in entropy from mixing, that would be defined as S minus S star, where S would be the entropy before or after mixing, and the S star would be the entropy before mixing. So delta G mixing, of course, would still be equal to delta H mix minus T delta S mix, since delta G is equal to delta H minus T delta S. This would be assuming constant temperature, obviously. Now remember, some of this is due to intermolecular forces, and some of this is due to intermolecular forces in entropy. Delta V mix, delta U mix, delta H mix, delta CP mix, those are all from intermolecular forces. Delta S mix, delta G mix, and delta A mix, those depend on entropy also. We're now in physical chemistry, chapter 9, section 5. We're going to be talking about ideal solutions in the liquid or solid phase. Now, before mixing, let's say we have two different species, A bonded to A and B bonded to B. That doesn't imply atoms. This could be like a methyl group, so this would be ethane. But it could be an atom. This would be chlorine, chlorine, so this would be diatomic chlorine, whatever. So if the bond between A and A, the bond between B and B, is kind of like the bond between A and B, then we would say that's an ideal solution. Now, an example would be something like brass, because that's a solid solution to copper and zinc. Copper and zinc, they're similar enough atoms that, copper bonded to copper or zinc bonded to zinc is much like copper bonded to zinc. Now, there are other types of this. For example, let's say we have iodomethane made with carbon 12 or carbon 13. It's almost identical molecule, just slightly different. So these two together would be an ideal solution, and it could be in the solid phase or liquid phase. Likewise, if we have, let's say, some hexane, or some hexane but with an extra methyl group off the side or the end anywhere. Well, this one methyl group is kind of like hydrogen, just bigger, but it's still roughly the same shape. So a mixture of this regular methane and then, methyl, or hexane and methylhexane would be an ideal solution. And then, of course, let's say we have chloroethane and bromomethane, or ethane. Chlorine and bromine, they're in the same column of the periodic table. One's a little bigger than the other, but it's still roughly the same shape. So the mixture of these two would be an example of an ideal solution. Now, there, of course, would be a lot of substances that are not ideal solutions. For example, let's say we have A to A or B to B, and those two are different from A bonded to B. For example, let's say we have diatomic hydrogen, diatomic chlorine. Well,
this would be nonpolar, this would be nonpolar, but then obviously hydrochloric acid, or hydrogen chloride, whatever you want to call it, would be polar. So this would be a very different type of bond. Same thing, if you had hydrogen, oxygen, water, there's a little difference between oxygen and water. And likewise, if the size of the shape of A is not the same size and shape as B, like let's say, I don't know, one is like a ether, one is just nonpolar, mixing them together is not an ideal solution anymore because they behave so differently. They're discernible. Basically, if you can't easily discern them, separate them out in a mixture, it'd be an ideal solution. Continuing on physical chemistry, we're in chapter 9, section 5. What is the thermodynamic definition of an ideal solution? Well, there are several things we can say about ideal solutions for thermodynamics. One, we already showed before, that the change in the Gibbs free energy of the mixture is equal to RT, remember that's the gas constant, times the temperature, times Na, natural log of the mole fraction of A, plus Nb, natural log of mole fraction of B. Remember, N is the number of molecules of A, and Nb is the number of molecules of B. Delta U, the change in internal energy of the mixture, is going to be equal to 0. Delta V, the change in volume for the mixture, is going to be equal to 0. And so delta H, the change in enthalpy of the mixture, is going to be delta U for the mixture plus P delta V for the mixture. And those are both equal to 0, so this has to be equal to 0 too. So what this is saying, we're going to go from state 1 unmixed to state 2 mixed. So in state 1, we have A at a certain temperature and pressure. We have B at a certain temperature and pressure, the same one obviously. When we let them mix together, we're going to end up with A and B at the same temperature and pressure. That's why we had to say delta volume didn't change. We know delta T and P are not going to change. Now, this is assuming, of course, that A and B, the molecules or species, whatever they are, the same size and shape. Now, the change in entropy, remember, is going to be the entropy of state 2 minus the entropy of state 1. And again, we showed before, when we talked about absolute entropy, that's going to be equal to K times the natural log of probability of state 2 over the probability of state 1. Remember, K is the Boltzmann constant. And it's still a P, but it's not pressure, it's probability. This is physical chemistry. We're in chapter 9, section 5 still. Remember, when we add the asterisk or star to a superscript to a variable, that means it's we're talking about what it was before mixing. For example, let's say we have VA star. This means species A, the volume before it was mixed. And then V here is the total volume of the mixture. So we have VA star over VA star plus VB star. So what this is saying is that the total volume is equal to the sum of the separate volumes. So it's like an extensive variable, basically. Volume is an extensive variable. Now we already know from before, the change in entropy is going to be equal to the number of moles or molecules of A times R times the natural log of the total volume over the volume of A plus the number of moles of B times the R gas constant times the natural log of total volume over the volume of V. This is assuming an ideal gas, which is what we're talking about for now. Now, what if we have a liquid mixture? We're going to have delta S mix. Now notice this is the same as that upside down, except so we pull a minus sign out. So the change in entropy of mixture is equal to minus the number of moles of A times R, that's the natural log, of the volume of species A unmixed divided by total volume, minus the number of moles of B times the gas constant, that's the natural log, the volume of species B unmixed divided by the total volume. And again, this is assuming an ideal solution. Now, since we're going to assume that A and B, they have the same size, they have similar intermolecular forces, and they're roughly the same shape, then we can say that the volume, molar volume of species A unmixed is equal to the molar volume of species B unmixed. Likewise, we know that the volume of A unmixed is equal to the number of molecules of A times the molar volume of A unmixed. And likewise, the molar volume of B unmixed is equal to the number of moles of B times the molar volume of B unmixed. So we get the total volume is going to be equal to the initial, or the unmixed volume of A plus the unmixed volume of B. So pulling this out, we get the number of molecules of A plus the number of molecules of B times the unmixed volume of A. Or you could rewrite it as the number of moles of A plus the number of moles of B times the unmixed molar volume of B. Works out the same. So we know that the change in entropy for the mixing is going to be equal to minus R, pull that out, times the number of moles of substance A times the natural log of the mole fraction of A, plus the number of moles of B times the natural log of the mole fraction of B. And this is just like we did when we talked about ideal gas at constant temperature and pressure. We're in physical chemistry, chapter 9, section 5. So now we know that the change in entropy from mixing is going to be equal to minus the number of moles of A times the gas constant R times the natural log of Na, the number of moles of A, substance A, times the unmixed molar volume of A divided by the number of moles of A plus the number of moles of B times the unmixed molar volume of A, and minus number of moles of B times R times the natural log of the number of moles of B times the unmixed molar volume of B divided by the total number of moles of A plus B times the unmixed molar volume of A. Now, let's say delta G mix is going to be equal to delta H mix minus T delta S mix. Now we can say that the change in enthalpy of mixture is equal to 0 for an ideal gas solution. Since the intermolecular forces are all the same, we're going to say that any intermolecular bonds you break are going to be equal to any intermolecular bonds that you form. Now, so the delta G mixture is going to be equal to 0 minus T delta S, which we had minus Na times R times the natural log of mole fraction of A, minus number of moles of B times the gas constant R times the natural log of the mole fraction of B. Again, this is for an ideal solution only. So just distributing out the minus sign, we're going to get the change in Gibbs free energy of the mixture is going to be equal to R times T times the number of moles of A times the natural log of the mole fraction of A, plus the number of moles of B times the natural log of the mole fraction of B. And this is out for an ideal liquid or solid solution. Now remember, R is equal to Avogadro's number times Boltzmann constant. I think we mentioned that when we first derived Boltzmann's constant. So that just means R is equal to Na times K. So R you can think of it as like energy per mole, and then K would be energy per atom. Another way you could find R experimentally is just take the limit as pressure goes to 0 of PV divided by NT. Now we're going to do a review of some of these other terms that we've been doing, make sure you understand what they all mean. So like mu sub I, we already mentioned before, that's chemical potential of substance I. And we've been talking about the change in Gibbs free energy of mixture. So remember that is equal to the absolute Gibbs free energy minus the Gibbs free energy pre-mixed. Talking about physical chemistry. We're in chapter 9, we're just starting section 6 now. So for our pure substance, we said that the molar Gibbs free energy of that substance is equal to mu, or chemical potential of that substance. And that, of course, would be the Gibbs free energy of the substance divided by n, the number of moles of that substance. Now, we said before that delta G mixture is equal to the sum of Ni times mu I minus Ni, the sum Ni mu I star. In other words, the sum of all the chemical potentials times the amount of each substance mixed versus minus unmixed. And that, of course, is equal to RT times the sum of the number of moles of that substance times the natural log of the mole fraction of that substance. And that's the sum over all the substances. That's what, remember, this sigma is summation notation. So we're going to have the sum over I, which is kind of explicit up here. But anyway, the Ni times mu I, that's going to be equal to the sum Ni times mu I star plus RT times the sum Ni natural log of Xi. So what we're going to do is we're going to distribute them, the summation notation, basically, combine the terms. So we get the sum of ni mu I equals the sum of ni mu I star plus RT natural log of xi. This is an I here, obviously. So mu I is going to be equal to mu I star plus RT natural log of the mole fraction of xi. Okay, so now we can talk about this formula here. This is our thermodynamic definition of an ideal solution. A solution is ideal if the chemical potential of every single component in the solution obeys this equation for any solution compositions, in other words, any mole fraction, and that for a range of temperature and pressure. This is Physical Chemistry, Chapter 9. We're continuing Section 6. So we're continuing what we talked about before about chemical potential mu sub I. We always want to compare that with what we would have with PV equals nRT, which was our definition of an ideal gas. So we have here a graph of mu for substance I, that's chemical potential, remember, against the mole fraction. When the substance gets down, the mole fraction gets down close to 0, mu sub I actually gets close to negative infinity. On the other hand, as mole fraction gets to 1, then of course it would approach what we would have mu I star, which was for the pure substance. And this graph is of course assuming that temperature and pressure are constant. Now, let's talk about the thermodynamic properties of an ideal solution. Remember, this is just a hypothetical model like an ideal gas. What's going to happen in real life could be a little bit different. So one, remember what our standard states were. We talked about this in Chapter 5. For a gas, it's a pure ideal gas. P naught equals 1 bar, and T is whatever temperature of interest we have. For a liquid, it's a pure liquid. P naught 1 bar still, and temperature is equal to the temperature of the solution. And we can abbreviate that SOLN for solution. And then again for solid, it's a pure solid. We still have P naught is equal to 1 bar, and temperature is whatever the temperature of the solution happens to be. Now, remember mu I star is the chemical potential for the pure substance. Now, on the other hand, mu I naught means in the standard state. Mu I naught is defined as mu I star at temperature and pressure. Mu I star means, of course, pure substance. I think we already said that 5 times. Mu I is equal to mu I star plus RT natural log of mole fraction of I. We showed that's true for an ideal solution only. And likewise, mu I naught is going to be equal to mu I star TP for an ideal solution. That's it. We're in Physical Chemistry, Chapter 9, continuing Section 6 now. Now we're going to talk about mixing quantities. So let's say we have the change in Gibbs free energy for mixing. That's just the Gibbs free energy of substance I after mixing minus the Gibbs free energy of substance I star. And remember, the star means before mixing, the pure substance. So rewritten based on the formulas we had before, the change in Gibbs free energy of mixture is equal to the sum of the number of moles of I times this quantity here. Gibbs free energy of the substance after mixing minus the Gibbs free energy, molar, of the substance before mixing. And this is at constant temperature and pressure. Now we also know, remember that the molar Gibbs free energy of substance is equal to the Gibbs free energy of the substance divided by n, the number of moles of the substance. So, taking that, we get delta G mixture is going to be equal to the sum of Ni times mu sub I minus mu sub I star. And we also know mu sub I minus mu sub I star is equal to RT natural log of x sub I. So, substituting that back in, we get the change in Gibbs free energy of the mixture is just equal to RT times the sum of the number of moles of the substance I times the natural log of the mole fraction of substance I. But again, this is assuming it's an ideal solution at constant temperature and pressure. Now, mole fraction, by definition, has to be between 0 and 1. If it was 0 or equal to 1, equal to 0, then it would be, there's no mixing. We're talking about mixing, so it has to be between those two. So that means that the natural log of x sub I is always negative. So putting that back into this formula, we're going to end up delta G of mixture is always negative. less than 0. And remember, our definition of spontaneous is we want to minimize the Gibbs free energy. Therefore, mixing is always spontaneous for an ideal solution anyway. Now, the change in volume of a mixture is going to be equal to the derivative of the change in Gibbs free energy of the mixture divided by with respect to pressure, holding temperature and the number of moles constant. But we said that delta G mix is independent of pressure at constant temperature. Therefore, that term is going to be, or the derivative at least, is going to be equal to 0. Therefore, the change in volume of mixing is going to be equal to 0 for an ideal solution at constant temperature and pressure at least. Continuing on physical chemistry, chapter 9, section 6. So the delta S mixture is equal to the derivative of the change in Gibbs free energy of mixing with respect to temperature, holding pressure and the number of molecules constant for each species. So pulling that out and substituting in, we get the derivative with respect to temperature of RT times the sum over I, substance I, and I, natural log of xi. The derivative of T with respect to T is just 1, so that'll disappear. So we get delta S mix is equal to minus R times the sum over substance I, or the number of moles of substance I times the natural log of mole fraction of I. Again, this is assuming ideal solution. Now, the change in entropy of mixing is going to be greater than 0. That's normally true. Now let's talk about an example of mixing two liquids, I guess. So HCCl3, this is called chloroform, and then CH3CCH3 with the double bonded O, that's a ketone obviously, that's acetone. Now the delta S is less than 0 for this one, but it's still spontaneous. Delta G is less than 0. Now, change in enthalpy of mixture, remember, would be the change in Gibbs free energy of mixture plus T times the change in entropy of mixing. So the change in enthalpy of mixing is going to be equal to RT times the sum over substance I times the number of moles of substance I times the natural log of substance I minus RT times the sum of number of moles of substance I times the natural log of substance I. These are identical terms, that equals 0. So what this tells us is that for an ideal solution, there is no heat of mixing, which should be obvious because you're not going to have any net change in intermolecular bonding. So let's say we have an ideal solution of A and B. We're doing Gibbs. What is this? Well, anyway, we've got energy per mole here, units energy per mole here, joules per mole. So we've got pure substance A, pure substance B. So notice we have the mole fraction of B, 0 to 1, or mole fraction of A, 1 down to 0. Now, the change in enthalpy of mixing for any mole fraction is equal to 0. For different mole fractions, up to a certain point, the T delta S term is going to be higher, but the delta G of mixing is going to be minimized at a certain mole fraction. I didn't draw this very well, but these two are going to add up to be equal to delta H is equal to 0. Now remember, delta S is in joules per mole Kelvin, so this T delta S term, that's in joules per mole, molar energy. We're continuing physical chemistry, chapter 9, section 6. Not exactly going to be on the final, but gold in the ocean, of course, is not metallic. It's a gold chloride, oral chloride, whatever you want to call it. Anyway, so the change in heat or enthalpy of mixture, remember, is equal to the change in internal energy of mixture plus P delta V of mixture, assuming constant P, obviously. Now, we showed already that the change in internal energy of mixture is equal to 0. Or no, we're saying that the change in internal energy is equal to 0 because we've already shown that the change in enthalpy of mixture is equal to 0 and the change in volume of mixing is equal to 0, at least for an ideal solution. Now, if the change in enthalpy of mixing is equal to 0 and the change in volume of mixing is equal to 0, though, that's not enough that we can conclude that the solution is ideal, though. You got to go back to our definition of ideal solution. Okay, now we're going to talk about vapor pressure in ideal solutions. So we know, of course, that for any gas, the partial pressure of that gas I is equal to the total pressure times the mole fraction of that substance I. Now we also know that our condition of phase equilibrium is just that the chemical potential of that substance I in the liquid phase is equal to the chemical potential of that substance I in the vapor phase. V we're using for vapor, not G for gas. So this is what it would look like in equilibrium. We have our system, we have our liquid phase and our gas phase. Liquid phase on the bottom because it's usually denser. So the Xi, or X1 liquid, X12 liquid, X3 liquid, there's a mole fraction for each substance in the liquid phase, but there could be a different mole fraction of the substance in the gaseous phase. Now for the gaseous phase, of course, remember we said our total pressure is just equal to the pressure of substance 1 plus the pressure of substance 2, etc., all the way up to the pressure of substance I. Now mu sub I liquid, that's going to be equal to the mu sub I liquid star plus RT natural log of Xi liquid. That's for an ideal solution, we showed that already. And then mu sub I in the vapor phase is mu I naught in the vapor phase plus RT natural log partial pressure of substance I over P naught. And that's we showed for an ideal gas mixture. So we're going to use transitivity of equality to set these equal to each other. So equation 1, we're going to say that the mu I star liquid plus RT natural log of I, substance I liquid, is equal to mu I vapor plus RT natural log of partial pressure of I over P naught. So that's because we're saying that mu I liquid star is at temperature and unmixed pressure is equal to mu I vapor unmixed in the temperature, pressure, partial pressure of substance I. Continuing on physical chemistry, chapter 9, section 6. So our second equation then, mu I liquid unmixed at temperature and initial partial pressure unmixed is equal to the chemical potential of the substance in the vapor phase of that temperature unmixed plus RT natural log of the partial pressure over P naught. And then remember before, last slide, we had 1, mu I naught is equal to RT natural log of I, mole fraction of I in the liquid phase, plus mu I naught in the vapor phase, plus RT natural log of partial pressure over P naught. We're going to take this equation and multiply by -1, so we get minus mu I liquid unmixed minus RT natural log of mole fraction of I in the liquid phase is equal to mu I vapor in the standard state minus RT natural log of partial pressure of I over P naught. Now we're going to take that form and add it to 2. So total we get mu I in the liquid phase unmixed at temperature and partial pressure I unmixed minus chemical potential I in the liquid phase unmixed minus RT times the natural log of the mole fraction of I in the liquid phase. And that's equal to mu I in the vapor phase at temperature, standard state, plus RT, natural log, of the partial pressure unmixed over P naught, minus chemical potential of I in the vapor phase, in the standard state, minus RT, natural log, of partial pressure over P naught. So we also know, okay, at low and moderate pressures, we're going to say that the chemical potential of the liquid star at temperature and Pi is just going to be equal to the chemical potential of I liquid star at any temperature and pressure. So what that means is we can simplify all this and just get minus RT times the natural log of mole fraction of substance I in the liquid phase is equal to RT times the natural log of partial pressure of substance I unmixed minus partial natural log of standard pressure, 1 bar, minus the natural log of partial pressure of I, plus the natural log of 1 bar. So simplifying that, rewriting it a little bit, divided by RT, etc., we get minus natural log of mole fraction of I in the liquid phase is equal to the natural log of partial pressure of I unmixed over the partial pressure of I mixed. We'll just multiply by, or no, flip this upside down to get rid of the minus sign. So we get natural log of mole fraction of I in the liquid phase is equal to the natural log of partial pressure of I divided by the partial pressure of I unmixed. Taking e to both sides, of course, we get mole fraction of I in the liquid phase is equal to partial pressure of I over partial pressure of I unmixed. Solve for the partial pressure of I, we get the partial pressure of I is equal to the mole fraction of I in the liquid phase times the partial pressure of I unmixed. That is called Raoult's law for the ideal solutions, and that's valid at low to moderate pressure. We're in physical chemistry, chapter 9, continuing section 6. So we know for the partial pressure of substance I is equal to the mole fraction of the substance I in the vapor phase times the total pressure. P is total pressure in the gaseous phase, or above the liquid phase. Now we know that X of I in the vapor phase times the total pressure then is equal to the mole fraction in the liquid phase times Pi star. Now for two component system, let's just say components A and B, with an ideal solution, we'll say, okay, the total pressure is equal to the pressure of A plus the pressure of B. So that's going to be equal to the mole fraction of A in the liquid phase times the partial pressure of A star unmixed, plus the mole fraction of B in the liquid phase times the pressure of B initial unmixed. And that's going to be substituting in XB is 1 minus XA, we get XA liquid times PA star plus 1 minus XA liquid times PV star. So simplifying that, or distributing that, we get the total pressure is equal to XA in the liquid phase times the pressure of A unmixed plus the pressure of B unmixed minus the mole fraction of A in the liquid phase times the pressure of B unmixed. So now we have the pressure of the solution is equal to PA star minus PB times the mole fraction of A in the liquid phase plus PV star. The reason we wrote it like this, even though these are all true of course, is that now we have it y equals mx plus b form, so we can graph it. Now of course if you were to put in 0 for the mole fraction of A in the liquid phase, then the partial pressure, or the pressure of the solution total is just going to be equal to the pressure of B unmixed. And likewise, if you put in 1 for the mole fraction of B in the liquid phase, then the pressure of the solution is going to be equal to the pressure A unmixed. Now, let's graph, let's graph now the pressure in the solution against the mole fraction of A. We're actually going to graph 3 here. We're going to graph the partial pressure of A. So 0A is 0 pressure, 1A, the total pressure, and vice versa. And then add those two together. Now this here, just to make it worth looking at, we've assumed that the pressure of A unmixed is greater than the pressure of B unmixed. So that's why this goes up higher than that side. It could have been the other way around, it doesn't matter. So these are the 3 functions that we plotted here, just like I said before. Continuing on physical chemistry, chapter 9, section 6. So we can say that the pressure of substance I is equal to the mole fraction of the I in the vapor phase times the total pressure in the, above the solution, or in the gas phase. We know that the mole fraction of I in the vapor phase times pressure is also equal to the mole fraction of I in the liquid phase times the unmixed pressure. Now for 2 component system, let's call them A and B, we're assuming it's an ideal solution. So we know that the total pressure is equal to the pressure of A plus the pressure of B. So that means the pressure is equal to the mole fraction of A in the liquid phase times the pressure of A unmixed plus the mole fraction of B in the liquid phase times the pressure of B unmixed. And that's equal to the mole fraction of A in the liquid phase times A unmixed times 1 plus 1 minus mole fraction of A liquid, PB star. Because all the mole fractions have to add up equal to 1, so we substitute it here. So the pressure then becomes the mole fraction of A in the liquid phase times PA star plus PB star minus mole fraction of A liquid times PB star. Then we're going to say, okay, so the pressure of the solution is going to be equal to PA star minus PB star times the mole fraction of A liquid plus PB star. And we did that, so now it's equal to y equals mx plus b, so we can graph it.
Now if the mole fraction of A in the liquid phase is equal to 0, then the pressure of the solution is going to be just the pressure of B unmixed. If the mole fraction of A in the liquid phase is equal to 1, then the pressure in the solution is just going to be the pressure of A unmixed. So this is what we're going to graph here. We have pressure here against mole fraction of A. It's going from 0 to 1, of course. So one graph here, we got the pressure of A, and that's going to be equal to XA in the liquid phase times PA star. So it starts from 0 and goes all the way to whatever PA star is times XA liquid. And then the other, we also have pressure of substance B, and that's going to be equal to the molar fraction of B in the liquid phase times PV star. And then here, we added them up together. The total solution is just the partial pressure of A plus the partial pressure of B. Continuing on physical chemistry, chapter 9, this is the end of section 6 now. As an example, a solution that is close to ideal would be benzene, which is C6H6. If you've had organic chemistry, I'm sure you know all about that. And toluene, which is C6H5, and then with a methyl group coming out the side. And again, if you've had organic chemistry, I'm sure you know all about that one too. So substitute P equals XAL times, let's read this correct. The pressure is equal to mole fraction of A in the liquid phase times the pressure of A unmixed plus the pressure of B in the unmixed phase minus the mole fraction of A in the liquid phase times the unmixed pressure of B. And we're going to substitute that into the mole fraction of I in the vapor phase times the total pressure is equal to the mole fraction of I in the liquid phase times the pressure of I unmixed. And then solving for the mole fraction of A in the vapor phase, we get the mole fraction of A in the liquid phase times the pressure of A unmixed divided by the pressure of A unmixed minus the pressure of B unmixed times the mole fraction of A in the liquid phase plus the pressure of B unmixed. Now this, of course, is not the formula for a line unless it happens that the pressure A star is equal to the pressure B star. Now this is what it would look like. So we have mole fraction of A in the liquid phase versus mole fraction of A in the vapor phase. Now if they happen to be the same, then you'll get a straight line going from 0 to 1. If it turns out that the pressure of A unmixed is 1/3 of the pressure of B unmixed, then it's going to droop down this way, which means you'll have less in the vapor phase. On the other hand, if it turns out that the pressure of A unmixed is equal to 3 times the pressure of B unmixed, then it's going to bend out this way, and you'll have more vapor phase in the higher mole fraction of the vapor phase than the liquid phase. Continuing on physical chemistry, chapter 9. This here is all of section 7 that we're doing. So we're talking about ideally dilute solutions. Now an ideal solution, this solution exists in the limit where the molecules of the different components resemble one each other very closely without actually being identical. And 2, ideal dilute system or ideally dilute system, the solvent mole fraction approaches 1. And the amount of the solute present is very small. Now remember, we're going to use capital A for solvent in this case, and lowercase I for our solute. So what these two are saying is that mu sub A equals mu A star at temperature and pressure plus RT, natural log of mole fraction of A. This means that the solvent is ideally dilute solution. And then the mu I equals mu I naught at T and P plus RT, natural log of XI. This means that the solute is an ideally dilute solution. Now, if we have an ideally dilute solution, then we can simplify and just kind of round to say, okay, that Xi equals Mi equals Ci. Remember, M here is not mass, and C is not specific heat. X is mole fraction, M is molality, and C is molarity. So concentration. So mu I equals mu I naught at Tp plus RT, natural log of Xi, or natural log of Mi, or natural log of Ci, which doesn't really matter. Okay, we're in physical chemistry, chapter 9. We're doing section 8 now. As we showed before, mu I equals mu I naught, which means standard state, temperature and pressure, plus RT, natural log of the mole fraction of I. Or we can use the molality or the molarity, because we're assuming ideally dilute solution. Now, let's start with the vapor pressure in ideally dilute solution. Here's our system. We have the liquid down here, and so we're saying this is ideally dilute, and then we have above it is our vapor phase, including presumably some of the solute. Now, PI is the partial pressure of the solute, I, in the vapor, and then P, of course, would be the total pressure of the vapor phase, gas phase. Now, we know mu I in the vapor phase is equal to mu I in the vapor phase at standard state and temperature, plus RT times the natural log of the partial pressure of the substance I divided by P naught. This is for an ideal gas mixture anyway. And then the mu I in the liquid is going to be equal to mu I naught plus RT times the natural log of the mole fraction of the liquid. And that's for our liquid solution. We're not talking about solids right now. No point. So if we set these two equal to each other, in other words, if we're assuming equilibrium, then mu I liquid is equal to mu I vapor. So using transitivity equality, we get mu I vapor naught plus RT natural log of Pi over P naught equals mu I in the liquid naught plus RT times the natural log of the mole fraction of I in the liquid phase. Now we're just going to do some algebra, and we'll say mu I in the liquid minus mu I naught in the vapor. This should be a vapor. Oops. Equals RT times Xi in the liquid plus RT natural log of Pi over P naught. We're going to divide by RT to get mu I naught in the liquid phase minus mu I naught in the vapor phase over RT is equal to minus ln Xi in the liquid plus ln Pi over P naught. So then what did we do? We're going to simplify these two, combine them into a natural log, one natural log using our rule of natural logs. So you get mu I in the liquid phase in standard state minus mu I in the vapor phase in standard state divided by RT is equal to the natural log of the partial pressure of I over the mole fraction of I in the liquid phase times P naught. Continuing on physical chemistry, chapter 9, section 8. So rewriting what we had on the previous slide, we're going to take E to both sides. So we get the partial pressure of I over the mole fraction of I in the liquid over P naught is equal to E to the mu sub I in liquid at standard state minus mu sub I in the vapor phase at standard state divided by RT. So we're going to multiply by P naught. So we're going to get Pi over Xi liquid equals P naught times E to the mu sub I in the liquid phase at standard state minus mu sub I in the vapor phase at standard state divided by RT. That's going to be equal to Ki of temperature and pressure. This means it's dependent on temperature and pressure. Ki is called Henry's law constant. So just multiplying this by Xi now, we get the partial pressure of substance I is equal to the Henry's law constant of substance I for that temperature and pressure times the mole fraction of substance I in the liquid phase. And this is Henry's law. Now Henry's law is used for dissolving gas and liquid. The solute, remember, is ideally dilute solution and ideal vapor. So this only applies for like really low concentrations. Now this is how they carbonate liquid as an example. And it only applies to a closed system, like a Coke can. Now if we increase the pressure, that means that the mole fraction of I is increasing, and therefore solubility is going to increase. Now, mole fraction of I is dimensionless, therefore Ki must have units of pressure. Now for H2, hydrogen gas is a solute. In water, Ki is going to be about 71.1 kilobars. But in benzene, Ki is going to be about 3.93 kilobars. Now higher Ki means it's lower solubility, because remember, the mole fraction of I in the liquid phase is equal to the pressure of I divided by Ki. Just rewriting what we had up here. Now temperature, it means we're going to, for water, it's going to decrease the solubility, but for an organic solvent to be the other way around. Physical chemistry, chapter 9, continuing section 8. We're almost done with the chapter, a couple more slides. Variation of gas solubility with temperature. So generally, as temperature increases, stability decreases. Now, one thing to keep in mind, Henry's law does not apply if you have a strong electrolyte, such as hydrogen chloride gas. If you take water liquid, and you have hydrogen chloride gas above it, try to dissolve it, what you're going to end up with is hydronium ions and chloride ions. This, of course, would be called hydrochloric acid. Also, Henry's law does not apply if the solute gas, it actually reacts with a solvent. So, I don't have an example, but if there's a reaction, it's not dissolving, it's doing something else. Now remember, the partial pressure of I is equal to Henry's law constant times the mole fraction of I in an ideally dilute solution. Now, one thing though, like helium is less soluble than nitrogen too. And so let's see, mu I is mu I naught plus RT natural log of mole fraction of I for non-electrolytes, like we said up here. Now, let's say we have ammonia and water. So I guess this is reacting ammonium hydroxide, but we would say ammonia is very soluble. Okay, so let's say we have increase in pressure here. We would expect from Henry's law the mole fraction to go up as a straight line. That's what this dotted line is. For comparison, if you increase pressure with hydrogen, it's linear up to about 200 atm, but then it curves down a little bit. So it's not as soluble as you might expect from Henry's law. So this would be like the limit of where Henry's law is relevant to hydrogen. Likewise, nitrogen, it stays linear until about 100 atm, and then it too deviates down. So again, that means that 100 atm is the limit to where Henry's law is applicable to nitrogen gas. Continuing on physical chemistry, chapter 9 is almost done with section 8 in chapter 9. So Raoult's law says that the partial pressure of substance A is equal to the mole fraction of substance A in the liquid times the partial pressure of A unmixed. Now, let's graph as an example chloroform dissolving in acetone. So here we have zero chloroform or pure chloroform or pure acetone, or zero acetone, pure acetone. Now the dotted line is the ideal that we already talked about before. Notice this is a straight line, this is a straight line, so this is kind of a parabola. It should be maxed about where they cross, I think. And then the continuous line shows what's actually happening. Notice this is below the ideal, this is below the ideal, this is below the ideal. This is called negative deviation. Now, this happens because acetone won't hydrogen bond to other acetone molecules, and chloroform molecules won't hydrogen bond to each other. But chloroform can hydrogen bond to acetone. Now, before I show why, remember this is acetone. Notice oxygen with its unbound electrons out here. And then chloroform. Notice chlorine is very electronegative. Now remember, we know oxygen, nitrogen, and fluorine, those are very electronegative. Oxygen is 3.5, nitrogen is 3.0, and fluorine is 4.0. Now to understand, here's how we get the hydrogen bond, one of our acetone molecules, one of the chloroform molecules. So we have the unbound electrons out here, and this hydrogen, since these chlorine atoms, they're very electronegative, the carbon is electron deficient, which means that it's kind of going to take up the electron cloud from the hydrogen, giving the hydrogen a partial positive charge. So with this partial positive charge out here, and then the unbound pairs of electrons, we get hydrogen bonding in here. So this is what's causing the deviation down from ideal. Okay, physical chemistry, we're finishing up chapter 9. This is the end of section 8. We showed before an example of negative deviation when you mix two different substances. Now we got positive deviation. So we're mixing CS2, I don't even remember what that's called, and acetone. So again, the dotted line here, these are supposed to be straight lines. These are ideal. And then the actual is going to be the solid curves. And as you can see, both the individual and the total pressure is positively deviated. Now in this case, the reason is because CS2 is not a polar molecule. Acetone is polar. So you're trying to mix unlike substances, that's all.